for Open Ecosystem team at Intel. You can learn all about us at open.intel.com, or you can learn about us at our podcast, which is open.intel.com/podcast. If you want to be a guest on the podcast, reach out to me on LinkedIn and we'll get you as a guest over there. So we are always looking for wonderful speakers around open source. This is our series where we are educating you about all the optimizations Intel has done in upstream projects. Well, not all, at least majority of the optimizations that are done in the upstream projects, and how they are made available to you in M7i and C7i instances that were just launched on Amazon. M7i, C7i are really the seventh generation of instances at AWS that are based upon Intel's fourth gen Xeon processor. And today I'm bringing a speaker, and that topic is very, very close to my heart. Well, let me introduce the speaker first, and then we'll get into the topic. Hi, Derek.
Hi.
Excellent. Derek, you want to introduce yourself?
Sure. So I am the Java Performance Manager here at Intel. I work with the sort of larger engineering team that works on Java OpenJDK optimization and analysis and hardware issues.
Beautiful. Well, so you can understand why I'm so excited, because really back, gosh, almost 25 years ago, I started my job at Sun Microsystems, and I was part of the original JDK team, and we were doing 1.1 or something like that release. It's been really astonishing on how fast Java grew and how well it has been adopted across the world. We talk about 12 to 15 million developers. I've seen the journey of Java being closed source, getting open source, OpenJDK building the momentum, and I've been deeply involved with the Java community. I'm a Java champion, as a matter of fact, right now. So this topic is very near and dear to my heart on how we are talking about it. So, Derek, this is super awesome, actually. You are a performance engineering manager for OpenJDK. What does your day job look like?
So my part of it has a lot to do with analyzing the performance of Java, finding bottlenecks in the system, finding how the system runs on Intel hardware, figuring out ways to make Java run faster, finding ways for Intel to run faster. So it's kind of going both sides of the problem here.
And the way you do that is by actually making contribution to the upstream. So you talk to customers, you understand what challenges, problems they are facing, and then you contribute those changes upstream to OpenJDK so that those things are integrated into OpenJDK.
Yeah. We don't have Intel doesn't have its own Java distribution. We don't have any particular need to do that. We want everybody to have the best performance that Java can have everywhere.
Right, and I think the keyword really is everyone, because we are really contributing to upstream OpenJDK in the main branch. That means any downstream distro, whether it's Oracle JDK, Amazon Corretto, Eclipse Adoptium, you name it, they're all getting the benefits. And the way this works is by making those upstream optimizations, or making those optimizations in upstream, when customers get the downstream distro, AWS, data center, network, edge, wherever you are running, you automatically get those optimizations.
Yeah. So, when you get the latest Java or even updates to LTS releases, we try and get as much goodness in those releases as we can.
This goes back to Pat's philosophy of software-defined, hardware-enabled. So, as customers are building their applications, Java applications using Java, yes, they're defining what the application needs to do, but it's really truly enabled by the hardware, and you are just bridging that gap that it is done in the most optimal manner.
Yeah. And the thing about Java being just-in-time compilation is that we can tune the code that we run or the code that we generate for the machine you're running on.
Right. Awesome. Okay, I know you have some slides as well, so let's dig into it and maybe talk about those.
Okay, great. Yeah, so the first one is just why Java is important to Intel at all. and it's because it's important to our customers. Right. So sometimes the customer's own workloads are running on Java, and so we want to make sure that that it runs well on Intel hardware. And then some of our major customers, for example, Amazon, it's important enough to them and to their customers that they in fact have their own Java team themselves that work on improving the system at the level that they look at. So there's a lot of straightforward Java applications that people run. There's a lot of open source platforms that itself are built in Java. Intel also sometimes, for a number of these, has contributes at this level as well. Spark and Cassandra and Kafka, etc. There's a number of benchmarks that are important for Intel, including spec power and spec JVD. So we make sure that the performance looks good on those applications as well.
So customer first is an Intel value, where it says, we listen to customers, we work with them, and we deliver on their needs. Back in 1970, Intel came up with the logo, Intel delivers. And that's what I'm seeing here, really. What you're telling me is our customer and their customer, because we got to be in this run together. When they win, we win. When they succeed is how we succeed. And that's the value that we are really showing here. So we're really, Java is 12 to 15 million developers, by far the largest language used in the enterprise. So we don't just contribute to OpenJDK to make our customers successful, but to all of these platforms as well. So we're doing optimizations at pretty much the entire stack.
Yeah, there's a lot of things that make sense at the JVM level, and other optimizations that don't make quite as much sense there, but in particular applications that really pay off.
Wonderful. All right, let's keep going.
So one of the things that, I've been in the Java industry since 1995. And so in some ways it's been doing the same thing, and it must get boring. But one of the things that's been really interesting joining Intel is this real synergy that we have between the Intel hardware side and the OpenJDK software, right? So the sort of most obvious thing that happens is new hardware features come out, new instructions, sometimes new performance characteristics, right? And so we enable those Intel features in Java. There might be new crypto instructions, or the AVX 512 whole suite of instructions. It's quite, it gives us a lot of ammunition to define more optimizations in the OpenJDK. But then another thing is that there's always new Java features going into Java as well. And so Intel, we do our part to help support those on our hardware. A major one of those being the Vector API. It's been a new thing. We've been working really hard to get great performance on that, the new API that will be hopefully coming out in a release or two. And then finally, we take take the performance we have, analyze performance on various Java workloads. When we understand, we can find bottlenecks in the system, we can find new optimizations to make, and then also feedback to the hardware teams on what they could be doing to sometimes not just make Java applications go faster, but Java as a proxy for server software, generally speaking, right? Where it's if you're going between like HPC and a Java application server, we're much more like almost any other server software that you might be running in an HPC system. And so that feedback goes back into the hardware teams. They use that for their projections and understanding of how they want to design the next systems. They come up with new hardware implementations and then new hardware features, and this kind of cycles around.
This is a beautiful virtuous cycle I see. As at Intel, we are thinking about the hardware features, which you are in the loop of how those features are created. Then as the features are being built, you are able to implement those features in OpenJDK and push them live in the upstream. So that by the time, say, Sapphire Rapids, which was our fourth gen Intel Xeon processor, was available in AWS as m7i and c7i. By the time m7i, c7i comes, you've already made those features, enabled those hardware features in OpenJDK, and that is available in the downstream distro. So for a customer, it's a straight out of the box, seamless experience. m7i is there, they download Amazon Corretto or Oracle JDK, and it just works.
Yeah.
That's beautiful, actually. And then what you're telling me is also, as you are looking at Java, as you are enabling more features on Intel, you're giving feedback to our hardware team that how could we make, so it's a full virtuous cycle, essentially. I just love this loop, actually.
Yeah, it makes my job really interesting. So
I can imagine, I mean, people might say 25 years is a boring time, but hey, I've been involved with the Java community for all these. I mean, you are involved with me for a few years longer, but Java has been the most vibrant language in my opinion. So I love it being part of the community.
Yeah.
Okay.
Let's see. So this kind of leads into kind of a number of things that we've been adding, contributing to OpenJDK. Right? So there's a huge number of things. And this is going over from different hardware releases and different Java releases. These don't all line up completely. They're only Ice Lake things. Sometimes work that we're doing for Ice Lake actually pays off for Sapphire Rapids as well. And there are other things that we do in later releases that can, for general optimizations that can, help hardware all the way down, and even cross-platform. We certainly are not averse to making optimizations that help everybody. If Java's running better, then that's better for everybody.
So this Sapphire Rapids, Ice Lake, Cascade Lake, these are our Intel code names. Like we just did the 4th gen Xeon that was codenamed as Sapphire Rapids. So 3rd gen was Ice Lake, 2nd gen was Cascade Lake, so on and so forth, right?
Yeah.
And then on AWS, if I were to look at it, there are different generations. So what was Ice Lake? Like, was that C6 or C5?
Yeah, Ice Lake was C6.
C6, okay. And then similarly, Cascade Lake has a similar number as well. So customer would be more familiar with that, but without realizing the underlying hardware is Cascade Lake, Ice Lake, or Sapphire Rapids.
Yeah.
Got it. And the other thing that stands out to me here is I'm seeing this chart from Q3 18, like how we have been contributing to JDK 11 LTS. So JDK 11 was LTS probably before that, but we have been contributing in OpenJDK for more than a decade.
Yeah, definitely.
Okay, beautiful.
Yeah, so there's we can talk just briefly about some different categories of these operations. So there's a bunch of vectorization operations we have here using AVX 512 and other things to help optimize a bunch of different bits of functionality in the system. Sometimes they're very specific, like vectorizing the sine function. Right? So you can do, if you're doing getting sine or cosine of an array of numbers, you can just crunch this much faster. And so those pay off great if you happen to be doing sine or cosine. They can pay off a lot. There's other optimizations in here though, like string and array hash optimizations, which pretty much everybody uses strings, right? And hash it, or clear memory, or inlining various object copies sorts of operations. So some of these optimizations kind of have a broad influence across the entire spread of programs.
So what would if you go back to a previous slide for a second, what would the AVX 512 vectorization use case be? Like, what would customer use it for?
And all these optimizations here, we're optimizing various Java APIs that are typically processing chunks of data in arrays, bunches of data. So it might be for bit count optimizations, or various kinds of logic operations, or reverse bit operations. Right? And so instead of doing that byte by byte or word by word, we can actually do it, depending on the machine you're running on, up to 512 bits at a time, which in about the same cycle time as doing it byte by byte or int by int. So it can be, especially if you're as you're doing a very large operation, it can be much faster, 2 times, 4 times faster.
And so what API would, like you said, you made these optimizations to AVX 512 vectorization, but what Java API you said would be impacted by this? Like which of the Java API would be there?
Yeah, so there's a whole bunch of them. So some of them, some of these are basic math operations. Some of these are crypto optimizations. So some of these are crypto optimizations and checksums. So these are a mix of optimizations using AVX operations or new hardware instructions specifically for CRC processing or AES processing.
So the thinking here is that we are doing optimization at such a fundamental layer that such a lower layer closer to the hardware where it's impacting other upstack APIs as well. And so a lot of the Java language stack can actually leverage those optimizations.
Yeah, and these are things some of these can be, like I talked about, the sine and cosine. They may be very specific to some operations, but there's a whole lot of server operations that need to be doing crypto work or hashing or other kinds of encode decode operations.
And maybe the way to think about this is, yes, you are doing 2 to 4 times improvement in crypto or hashing, but when you are running an application, your total application would not improve by 2 to 4 times because only the crypto part. So if you do the profile of your application and your crypto hashing is about 5 to 10% of your application, that part would improve by 2 to 4 times.
Yeah, and the 2 to 4 was. I don't think we have numbers for crypto specifically that match that, but theoretically, just AVX, generally speaking, can just process numbers 4 at a time.
Got it. And those are again in lab conditions, so customers have to really try it out by themselves how it works for them.
Yeah, and we have some benchmarks that we'll show a little bit later to talk about some actual numbers. Shoot, I had a great idea, but I just lost it here. Okay, so maybe let's go to the next slide. You're talking about a couple other things. Right, so here's some more. These are actually the math optimizations here. Also, the vector API implementations going on, as well as base 64 encode and decode. And this is very heavily used when people are encoding binary objects like pictures within HTML or JSON type workloads. So it can be pretty common operation.
And so what I'm seeing is a similar theme, that really optimizations at a fundamental level that are helping other libraries in JDK to be more efficient.
Yes. Oh, and I remember the thing I almost forgot. So one of the things that we've done is we've been adding some of these vector operations for AVX 512 for several releases now, and the m7i instances actually do a much better job running those AVX 512 operations at full speed. So some of the operations we'll see some performance improvements for that show that, and some of the performance optimizations we've done on top of that are changing the tuning to use AVX 512 more often on the m7i instances, or the Sapphire Rapids generally, than we used to in the past, because there's less downside and then more upside.
Got it.
And once again, it's the same Java code. The JVM just can say, okay, on this hardware, we're going to do a little more like AVX 512. If you're on this one, we'll tune it down a little bit and get the best performance in this piece of hardware.
How do you decide rather the optimization goes in the JVM versus the language itself? Or are we primarily focused on the JVM part of it?
Yeah, mostly we want them to be in the JVM because it's a level of detail that we don't want the programmer to have to worry about so much. Right?
Yeah.
And
I think that's the beauty of it. That again goes back to sort of the customer first mindset, that no matter what hardware you are running at, if you are using the OpenJDK JVM, then it'll do the right thing for you automatically. I think that's the key element here.
Yeah, and our users code are dealing with a whole nother level of complexity above that, right? So there's enough complexity in their world. So we don't need to have them thinking about AVX 512 instructions or that sort of thing.
Right. Yeah, let's wrap through this slides, and I have one more question that I want to ask. Oh, actually, maybe that now is a good question. So on the JVM topic itself,
Mhm.
now you're making these optimizations in JVM, and that is definitely helping the Java language. How does it work with other languages like Kotlin and Groovy and Scala? Does it help those languages as well?
That's a little more complicated question. It's not. I don't know enough about how they're implemented. Some of them, I think, will quickly jump in and use the Java APIs to implement their own APIs or their own functionality. And in that case, if we've optimized the Java API, then they'll get that automatically. And similarly, other kinds of work we do with very some of the very basic operations, like array copy, system.array copy is to function. It's like memcopy or something else. There's a lot of optimizations you can do on different hardware to try and move bytes as most efficiently as possible. And now, I mean, any language on top of the JVM will probably take advantage of that.
That makes sense because depending upon how the language is implemented, on top of that, is it a interpreted language? It is a JIT language? What kind of language it is? What features it is using? Is it using the JVM directly, or is it going by the API? So the optimizations could vary widely, but by being in the JVM, it is available and accessible to everybody.
Yeah.
Okay.
Right, and this is just taking a little bit of look, comparing performance on different instance types, the m6i and the m7i with same JDK version. We're able to see 20, 40% improvement on some of these, some of them a little more than 2x. And it has to do with either new instructions on the new hardware or better performance on the new hardware, including, like I talked about before, specifically able to use some of the new AVX512 instructions in more scenarios. So we're getting some nice performance boosts, much more than your simple, the Gen IPC performance would boost would tell you.
So pretty much, base 64 decode, encode, functions, checksum, crypto, like these are something that you're doing in your application, right? And not just in application, but potentially frameworks like Cassandra, Spark, Kafka,
Yeah.
they are leveraging these applications as well. So such a fundamental change, which is helping make the entire Java ecosystem better, faster, more performant. So I think that's how I see it. Is that the right way of summarizing it?
Yeah. I think the most of the operations we've shown here. Well, I guess we did list some of the math functions. So if you're doing math, we're certainly doing a much better job on that. But a lot of these are actually fairly commonly used in server applications. So you should get some nice performance boost by that.
I think somebody was asking me the question, and I think we came up with this conclusion that how is Intel relevant to Java, somebody who's building a serverless application in the Java world? The discussion really went about this way, and eventually it was like, you want to run your Java applications in, say, AWS Lambda, right? That's the serverless platform. If you want to run it over there, the fact that at the back end is going to be running on an Intel hardware, and the fact that it's going to be using whatever Corretto, whatever runtime is going to be using, the fact that it's optimized for the hardware, that means it's going to take that much less memory, that much less compute power. And if each of your Lambda functions, so to say, could be 10, 20%, 30% efficient, take less memory, so that will actually bring down your cost right away. So it's really think and pay attention to where your Lambda functions are running and what platform are you using.
Yeah, I think that's what we're trying to do, is make sure that the job performance is there wherever and however the user's using it.
Right. Okay.
So stepping up a little bit higher level than this, looking at the new Java Vector API, which is getting ready to be finalized fairly soon. There's been quite a number of iterations of this. So they worked out what the API should look like, how should it be implemented. But the basic functionality it lets you do is it lets you actually write code in Java that can take advantage of the vector instructions in the hardware without actually having to write machine-specific code. So this can run on Intel with AVX2, which is 256-bit operations, or AVX 512, or on ARM with scalable vector extensions. And so it really brings the power of chewing through much more data at the same time up to the end programmer. And the really exciting thing is, we've been working on trying to implement this for a long time, but now we're seeing people actually using this, writing just Java applications. And for example, there's a m7i JSON library, which has been ported to use a vector API, and that's they're getting numbers like 2.8 times faster than Jackson. Elasticsearch has been doing some work on their vector similarity primitives and seeing 7x faster, 30% better indexing, which is overall. So there's a number of projects out there you can find on GitHub or other places which are really starting to take advantage of this. And once again, this will be, it runs on a number of different x86, Intel, AMD, or ARM-based hardware. We can all take advantage of this so that the user doesn't have to worry about the details.
That's beautiful. So this is a Java API that was incubated in JDK 16, and then at some point in the future, it will be part of LTS as well.
Yes, yeah, and so they've been adding new APIs, getting a better understanding of how they want to structure the data, and it integrates in with other Java language features. So they're also incubating. So they're sort of waiting for them all to merge into one cohesive whole that works really well together.
Got it. And then maybe the request or the call to action is for folks that are building applications where they can leverage this vector API to use it, because we're already seeing results in m7i JSON, Elasticsearch, and Parquet decoder.
Yeah, those are quite significant performance differences. So if you have a bottleneck where you're processing a bunch of data in some way, it can make a real big difference.
And I see there's a link to the JEP 338. So people want to read more about the API itself, they can do that there, right?
Yeah. I think that's the base level first vector API, and then there's been additional JEPs for each iteration of that.
Got it. Fantastic.
Yeah. And a final thing that we've been doing is, independent of new instructions in hardware, just across the industry as a whole, we've been adding more and more cores to CPUs. Right? So more cores, more problems. And so that's the really obvious ones. If you have a bunch of threads that are all locking the same lock, you get lock contention. That can be a performance problem. And some ways that's going to be a bit easier to track down. Various tools will help you find those pretty easily. But there can also be true sharing and false sharing sorts of bottlenecks where multiple threads and cores are accessing the same variable, or they're accessing different variables that happen to be on the same cache line. And these can be a bit trickier to track down. The software can often be rearranged slightly to avoid these problems. So we've been, as part of performance analysis, we've been looking at finding these bottlenecks in the system. And we found actually 3 different cases, one case in machine code, one case in C code, and one case in Java code. But they all have a same flavor where there's a sort of a hint that the system keeps around. So in one case, in the Java symbol table lookup code, there's actually 2 symbol tables, and it keeps track of which symbol table found the answer last time, and assuming that maybe that's be the best place to look for the next symbol. So it caches which one to look from. And that works really great until you have 60, 120, 240 virtual CPUs all trying to update that variable at the same time. And so we saw a bottleneck with that. It actually showed up in the spec JVM0 benchmark, but it's a critical part of class loading and object serialization. So it can really be an actual bottleneck to people's programs. And so in that case, we replace the shared variable with the thread local variable, and the problem went away. But it's a kind of thing that we've seen, a common idiom. We've seen it enough times in the JVM that it also might be present in the application libraries the platform using, or even the user's own code. So it's something to watch out for when you have these sort of hints that you're trying to optimize things, but in fact the optimization can cause a problem at scale.
My God, so more cores, more problems. You're right. So, and each core, if you're running multiple threads, that further makes the mission that much more complex. I think I'm really glad that we are doing that for our customers, detecting these problems and then trying to just integrate them at the lowest layer again so that they can be successful in their workloads optimizations. So this is wonderful, actually. And I know this is your last slide, I believe, Derek?
Yes. Yeah, I think so.
Okay, so I'm going to hide the slide here.
Yep.
So I guess going back to our conversation, for customers who are building application on m7i, c7i, for them, they can just download whatever OpenJDK distro that they care about, whether it's Oracle JDK, Amazon Corrado, Eclipse Adaptium, whatever, and that would just work out of the box for them. They will get these optimizations.
Yes. Yeah.
Okay, perfect. Is there anything else that I should have asked that I didn't ask you?
Anything? I'm drawing a blank. You were pretty thorough, I think so.
Okay, I really enjoy the conversation, and really the whole purpose is I'm talking to wonderful people like you around the world, and I just want to share these presentations with the wider world as well. So hopefully customers will find some good value insight out of this, and they will be able to continue leveraging the m7i, c7i instances on AWS. Derek, I really enjoyed the conversation. Thank you so much.
Okay, thank you, Ruth.
All right, I'm going to end the stream here. Bye-bye.
Bye.